right? So just to summarize, we have LiDAR canopy biometrics. We have vertical distribution, which are moment-based. We use moments, statistical moments, if you will, to characterize the vertical distribution. We've gone to L moments, what we call L moments. There are different types, different methods for describing statistical moments. And we use L moments. They're quantile-based. They're actually quartile-based, as opposed to percentile-based. And why this is good is because we avoid outliers. And so our models are much more consistent, and as such, we get better statistical models with these. Oops.
Question. Is it from your data, those spectral diagrams? Is it from your data, or?
Those spectra? No, I stole those. I stole those from Rob Green at JPL. He doesn't know it. So I showed this to my class yesterday. I had a lecture at 3:30 and I had to catch a 6 o'clock flight, so I ran out of there. But I showed this to him and I said, you know, nobody on this planet can generate spectra as clean as this. All right? You'll never, ever, ever, ever see spectra this clean. The only people who can do this are the guys at JPL. And they got like $1 zillion to work with, right? So they build spectrometers which are $5 million a copy, right? Whereas we don't use those. Right. So we use moment-based metrics, and the horizontal distribution of the canopy, we use gap measurements. We use at the top, we use a rugosity measurement, which is sort of the bumpiness of the surface, and then we use a canopy gap fraction, which looks at the number of points and the penetration. And we can split that up into very, very detailed gap distributions within the canopy as well. Terrain-based metrics, we have first-order shape-based metrics. These are all derivatives, so slope, aspect, curvatures, or slope curvatures, aspect. And wetness, which is complex. And then we upscale these to the same resolution as we developed for our biometrics using texture-based metrics, so grade level co-occurrence metrics, so mean, standard deviation, homogeneity, whatever. All right, so this gives us really an image cube, in the sense of the word, with about 30 or 40 metrics that we can use if we combine both of these. On the spectroscopy side, we have spectral metrics, we have band ratios. We all know what band ratios, they can be simple, they can be complex, NDVI is one of them. These are narrow band ratios, right? Because we have 2.5 nanometers or 5-6 nanometers to work with. We don't have to use the 150 nanometer, 200 nanometer wide windows that Landsat or Spot or any of these other guys use. So they're very, very detailed. They can be very targeted ratios. We use derivatives, so we look at the curve, the spectrum, and we generate first and second derivatives, third derivatives of that to look at the slope, the curvatures, etc. And that can be useful diagnostic metric. And we use what's called a continuum removal. So the continuum removal is kind of neat because what it does is it normalizes these absorption features in here. And it standardizes so we can compare them between spectra. And once we do that, we get a series of shape-based metrics. So we get the center, we get depth, we get areas. And with these, we can look at symmetry between the two sides, and it tells us an awful lot. So this is what we can get now. This is our first stage information that we extract from the data. Right. So once we do this, again, this is just another graphic to show you what we can do with this. So with the LiDAR, we have bare earth. We generate all of these different products. The canopy data, we do canopy mass, which gives us what we've been talking about. Individual stem and crown mapping, and I'll show you what we do with these later. And these are pretty neat. And again, the stem mapping is so easy to do. It really is. And then from the hyperspectral processing, we do species identification, we do foliar functioning, and pigment concentrations, etc. So basically just a summary, same thing. All right, so what are we going to do? I'll show you some examples of what we've done with some of this now. First year we had a spectrometer, we came out and we flew a little area up in Lac La Biche. I'm not sure why we went up here, but we came out here anyway. So we flew, it's about 20 square kilometers in Lac La Biche. I think it was for our tour. And this is it here. All right, so this is the spectroscopy data. And we flew LiDAR as well. And we clustered the LiDAR. So we generated these metrics, or similar metrics to what I just showed you, the LiDAR metrics. And we just ran a cluster analysis, so unsupervised. Most of you have done a remote sensing class, right? So you know what an unsupervised classification is. So we just ran an unsupervised classification on this, and we came up with a series of clusters. And these clusters were very, very indicative of the species distributions in there, because the species in the boreal mixedwood is very much structurally defined. Like you can look at the canopies, and the canopy structures are unique to certain species. Right? So we get these purples and blues in here, which are very much indicative of the aspen, poplar, balsam poplar stands in through here. The yellows and light greens in through here are conifers, probably white spruce, subalpine fir, possibly white spruce. And then we get these, can't really see them, these browns in here are jack pine stands, right? So this is this little lake right down in here, and you get browns all through. These are all jack pine stands in through here. And then there's some black spruce, and then we have wetlands and blues in through here as well. And the neat thing is we were looking at the LiDAR data when we first got it, and we looked at some of these little water courses here, and they were stepped, and we thought, my God, what is this? Right? And they were all beaver ponds. They were all beaver dams in through, and they're about a half meter to a meter, and they were stepped all the way through. And we thought the LiDAR data was hoot, but no, we looked at them and you can see these little lakes here, and there's a little beaver pond here, and there's a beaver pond behind here, and so anyways, it's pretty neat. So then what we do is we take this cluster, and then we superimpose it back on our metrics, and we do a random extraction of points, and we summarize them. So for example, these represent the classes with approximately the same colors, and we can summarize their distribution. So we look at let's say we look at these deciduous stands up in through here. They're the tallest. Their average is about 22 meters. Right. And here's the variance. The skewness. Now the skewness is kind of interesting because when we have a negatively skewed distribution, that means that most of our canopy points are concentrated at the top of the distribution. When it's positively skewed, they're concentrated at the bottom of the distribution. Right. So our deciduous, for example, have the most negative, right? So most of and as you would expect, right? Most of the points are concentrated at the top of the distribution. Kurtosis, again, it's a complex metric. It's sort of higher moments, so they tend to be a little bit noisier, but they do give us some indication of the shape of the distribution. But the gap fraction was interesting. We had a very low gap fraction for these two, and we had a higher sort of mid-rugosity, so it wasn't very particularly bumpy. The jack pine, which one's the jack? This, I think, is the jack pine right here, is about 10 to 12 meters. It has a skewness which is going towards bottom loaded, and then the gap fraction is very high, which is what you would expect because it's an open canopy stem, right? So we can tell an awful lot by just looking at the summary statistics, and this is only using our LiDAR metrics. So this is the first thing we did. We were pretty proud of this, actually, working on 20 meters. We've evolved, as most of us have. We're now incorporating more than one sensor. And so we're now looking at we did have hyperspectral as well, but we didn't really get into it for that project. We're now looking at treetops and using the treetops to help us define the ecology or the, not so much ecology, but certainly the species distribution and some of the issues with specifically related to forestry. This is a small area on King Island on the central coast, north of Vancouver Island. And we flew a larger area, flew about 6,000 hectares here, but this is a small subset of this. And here is the DM for this area, hill shaded, slope gradient. Our soil wetness index, that's what this looks like at 2 meter or 1 meter resolution, and our aspect, which is linearized. All right, so these are the terrain metrics that we generated from this. what we did was we using the LiDAR canopy data, helicopter data in this case, we extracted the treetops from this, and we mapped the treetops. And then we take those treetops and we superimpose them on top of the hyperspectral data. Right? That's what this represents here. Right? Now what we have is we've gone from, and then we extract a spectrum for each one of those treetops, one spectrum. So now what we've done is we've gone from basically an XY image, or several images, flat, well, I mean, they have some positioning information, but they're essentially just rasters of data. And we created a tree list. And with these data, we're probably, depending on the social position of the trees, but we're probably mapping about 75 to 80% of the codominant and dominant trees in there. We have an X, Y, and a Z. With allometric information, we can then generate a diameter. We have a spectrum. We can get species from that spectrum, right? And then what we end up doing is we end up mapping something that looks like this, and we map this back in image space. And what you see here is you see species information. There's a lot of, this is a really nasty data set to work with because it was cloudy and it was windy and the helicopter was just all over the planet. But so we have areas here where we don't have very much viable information, so we've just left it blank. But what we have here is we have individual treetops with species. And our species are probably in the order of 70, 75% accurate, okay, based on what we've been able to observe, depending on the species. Our cedars are very accurate. The separation between hemlock and spruce is probably less so. Pine, there's a few pine in here, but not many. But what we've also done is we've then developed a volume metric. So we have the height and we have the DBH. We apply a taper equation to that, and we get a volume per tree per species, and we map that. And so what we've done is we've proportioned the treetops to represent volumes. So where we have the bigger blobs, for lack of a better word, are the higher volume trees. Right? This is all I want to give them. I don't want to give them the actual volumes because they're going to do what we've done with the forest inventory maps for forever, is go into a polygon and say, why isn't this there? Why isn't this tree that you say is 400 cubic meters? We only measured it at 250 cubic meters. Why are you wrong? Right. So what we'll do is we'll say, look, here's a good area where you're going to find some large cedars, you're going to find some large spruce, and you're going to find some large hemlock or large balsam. and up in through here, the stuff is much smaller, so I'd stay away from that. If you're going to come up with a harvest plan, you stay away from that, right? Because it's just basically just scrub. You're not going to see that. If you go and look at this, you're not going to see that. What we've been able to do now is with a single flight and with an incremental amount of additional processing, we're able to get to this stage here where we can give them species and approximate volumes and locations. So they can go out and they can start surveying these areas and come up with a much better idea. They can avoid these areas into here because the trees are so small it's not worth their while. That was one filter, that's a treetop filter, and the treetops are really easy. We use a raster, we use a canopy height model, 1 meter, and we just use a local maximum filter on it. We just look for peaks. We've made it a little bit more complex because what we do is we look at a height-size relationship as well, so that bigger trees are not mapping multiple crowns within a large tree. But relatively simple. Here's another really simple way of using the LiDAR, integrating the LiDAR data with the hyperspectral data, is we use the LiDAR data, again as a filter, but as a height filter. Right? So here's our canopy height, 2 meter resolution. What we do is we determine what the top of the codominant canopy is, because that's where our pixels are the brightest. Our hyperspectral pixels are the brightest. That's where our highest signal to noise is, where we're going to get the most consistent and useful information. 85th percentile we've found to represent the top of the codominant canopy, empirically. all the work that we've been doing over the past 7 years, it's pretty much consistent at the 85th percentile. And so in this case, let's say it represents 20.7 meters. We take all of the heights that are 20.7 meters and higher, we keep those, and everything else gets set to 0. We lay that on top of the hyperspectral data, and we retain only those pixels. Everything else is 0. Right? What that does is it gives us an image where we're only mapping the top of the canopy. We're not worried about the stuff that's right underneath it, where there's shadows, where there's maybe more bark, so that the noise and the inconsistencies start to come in, and we start getting classification accuracies which are less than ideal. It starts to compromise all the work that we're doing. Even though the work that we're doing is good, all that stuff underneath it really does do nasty things to it. So that's the one level that we do. We also have another, in this example I'm going to show you, we also had another 2 filters that we used, both with LiDAR height. One was at 2 meters and the other one was at 0. Right? And we applied this to this area. This is up in the northeast corner of BC, Fort Nelson area, just north of Fort Nelson in the Horn River Basin. A lot of gas exploration and gas production going on. And this is for BC Oil and Gas Commission. And what they were interested in were a number of things. They were interested in wetlands mapping. They wanted trafficability. They wanted to look at their seismic lines and whether they could reuse seismic lines more than once, or whether once was enough and they had to rehabilitate those and cut new lines. They wanted to look at water availability, surface water availability, near surface water availability. They initially wanted us to look at these lakes in here and see if we could come up with some indication of depth. And that was one of the questions earlier on about bathymetric LiDAR, but these are so opaque. There's so many tannic acids in these lakes, and I'm sure you get the same thing up in northern Alberta that you're not going to see anything. And bathymetric LiDAR in these cases won't work either, because to answer the question that Nicholas couldn't answer, the bathymetric LiDAR is typically good to about 2 to 3 times a Secchi disc depth. All right, so if your Secchi disc depth is a foot, then the bathymetric LiDAR is going to go down 2 to 3 feet. So use that as a measure. So each one of these we flew these in 2009, 1st of September and 24th of September. I say here that they were for seasonality. That's wrong. I mean, that's a lie, really. It was because the weather was so crappy that we couldn't get back up there until the 24th again. But we flew 300 square kilometers in each of these 2 days, and 2 different areas completely. And so we did 2 different analyses. We did our initial wetlands mapping and species discrimination on this block here, and we looked at superficial and geomorphology and aggregates, which was the second objective. I'm not really going to talk that much about that today, because other people are going to talk about that. But we looked at aggregate mapping in this area here as well, in wetlands. So we did what I showed you before. We did our clustering, we did our canopy biometrics, we did our soil wetness clustering, and the soil wetness clustering didn't really, it's not immediately apparent what we got, but this is what we got out of it. Doesn't really show an awful lot in here, mainly because of the colors that I picked were not particularly great. But if we sample it, I sampled this randomly, and we came up with a series of classes, cluster classes, and soil wetness metrics, so mean, variance, homogeneity, and you can see as we go from class 1 through 5, we get a continuous increase in soil wetness mean. Class 5 are these lakes and very, very, and probably peripheral to the lakes. And then the variance increases as we get from dry to wet, and I'll show you how that looks in a minute. And then, of course, the homogeneity would then decrease. So those two are pretty inversely correlated. The canopy metrics look something like this. Again, they're probably meaningless, but we had 9 classes in here, and here we did the same thing. We looked at the height, gap, rugosity, and skewness for each one of these, and so we described those. So far, we haven't put much meaning to them, right? And then what we did is we went into our version of HEL in BC, which is our VRI, which is like your AVI, and we extracted species from these as best as we could, and we mapped them based on the wetness clusters and the veg clusters in through here. We looked at aspen, for example, birch, tamarack, larch, and then the conifers down in here, pine, white spruce, black spruce. So sort of typical. We didn't look at any of the grasses or any of the shrubs. These are just the tree species. And then what we did was we looked at the distribution within these clusters. So obviously, cluster 4 and 5, you're not going to get any tree growth at all because they're just way too wet. Cluster 3, you get some, but not very much. And it's clusters 1 and 2 that where you get. So we probably should do a little bit more separations on 1 and 2 and try to refine those a little bit better. But having said that, the spruce trees, if we combine the veg clustering with the wetness clustering, you can see that we're starting to pull out various species based on that. Not all that well, but so we applied our hyperspectral data. Deciduous, coniferous, herbaceous, and water. That's all we needed to do and separate the optical data. We fed those into the soil wetness index clusters and filtered them, and then we fed that into the LiDAR structure, and we came out with a final vegetation classification. Right? We have the filters I told you about, and this is what we ended up with. Can you see that? Oh, you can actually see that this time. This is the soil wetness index model. This is the canopy height model, and this is our final classification in through here. And you say, well, look at all these black areas, but all these black areas represent pixels that we didn't classify. We didn't classify them on purpose because they fell between the top of the codominant canopy and the 2 meter height. So in the aspen and poplar stands, these taller stands in through here, there are quite a few pixels down there that don't necessarily, that we're not going to classify at this level. But where we get the smaller, the black spruce, the open black spruce, and sedges, small shrubs, deciduous shrubs, we map all the pixels because the 2 meter and the 85th percentile basically match. And this is what we ended up with. So I was telling you about the wetlands. So here's a wetlands area. This is soil wetness index up and through here. We have peat hummocks. This is north, so there's discontinuous permafrost up in here. We have, what are these? I keep at you, be quiet. No, they're not Oxford. Lacey should know better than that. What are these? Does anybody know? Could anybody even guess? Northeast corner of BC. Northwest corner of Alberta. We get. It's muskeg, and what's a landform? Come on, all you geographers now. What is a landform that we get in permafrost? Pingos. Yeah, no, these are balsas. They're pingos. They're peat pingos. They're old peat pingos. You can see them. And what they have, what they promote are their little rises in better drained peat deposits. So we get taller vegetation on them. Here, this is the same one that's up into here. It's right there. Right? So we get taller vegetation growth. This is just, and if we look at the classification, it's primarily some deciduous on top. It's mixed deciduous coniferous on top, and then you go down into sedges, black spruce bogs, and sedges down through here. The lake in through here, we have a probably a marshy area along the edge of the lake before you head into small black spruce stand in here, and this is all mapped at 2 meters. And then open grasslands in through here, transitioning into black spruce bogs up into here. And then I think this shows the orthos that we fly as well with it. So here you can see, here's the lake. Here is this marshy area that we're mapping along here. You can see we're picking up these small pockets of sedges up in through here, and this grassy area with black spruce, and then we get into a greater extent of black spruce. This is this wetland area with these little turf or peat hummocks in it. So the detail at this point is quite extraordinary. The level of accuracy is quite extraordinary. And this is all automated. We're not sitting there with an air photo and, oops, it's got a mind of its own. We're not sitting with an air photo and drawing the polygons anymore. Okay, these are pixel by pixel, and they are very accurate. Right? But we wanted to look at this in a larger context, so we upscaled it to 20 meters. And this is what we ended up with. So this is the 20-meter resolution image for the 300 square kilometers, and you can see the same basic color. So here we have our deciduous, primarily aspen with some birch, balsam, poplar, I should say poplar with birch in through here. We have the light green is black spruce, the darker green is white spruce and pine, and then we have the sedges in through here. And lo and behold, what we came up with was we saw this really nifty network of wetlands in here, defined or connected wetlands, which represents a preglacial drainage network in through here. This is a dominant species VRI map for this area. And superimposed on top of this are sort of these immediate post-glacial surficial features. They're either recessional moraines, probably not because they're in the wrong direction. So they're probably shorelines, little beach lines. There's lacustrine deposits in through here as well, that are superimposed on top of these drainage networks, which is kind of neat, with different vegetation on them. And we see because there's a different type of conifer growth. There's probably white spruce pine on top of there as opposed to black spruce beside it. So it's pretty neat what you can do with it once you get up to the 20-meter resolution, and that's the hyperspectral data that corresponds to that again. The other area we looked at, we did the same sort of thing, but we were more interested in looking at aggregates, superficial mapping. So I'll just show you a couple of slides. Here's the elevation model representing this area. It's about 300 square kilometers, and we have probably, we go from 730 to 430 meters, so about 300 meters. It's not, the relief is pretty low, very flat. What we did was we ran the soil wetness index, and we put that through blue and green guns, I think, and then the bench height, the canopy height model, this is at 2 meters all in the red gun. So you can see, for example, all of these deposits in through here, we get high vegetation, primarily deciduous with some coniferous in through here. And they all, basically, if you look at this and you start mapping, you can start seeing these linear features. So we have all these recessional moraines going up and through here. We have old beach lines going through here, and we have the dune field down here. This is the classification again, scaled up to 20 meters, and so here, this lake here, and we can see the same sort of patterns. These are all wetlands in through here, deciduous, and we get probably a drainage divide in through, or not drainage divide, but a changing slope in through here, so it starts to drain more effectively away from that. Well, almost done. And this is the elevation model that goes with it. And if you look closely, you can't see from where you're sitting, but what you'll see is you'll see a series of dune features down in through here. This feature here has the highest vegetation in the area, so it's probably, if you look closely at it, if you zoomed in on that, which we're not going to do, we're looking at probably an outwash feature. It looks like the remnants of some sort of outwash terrace or cane terrace. Veg health, quickly. I know we're running out of time here. I was telling you about the spectroscopy. This is the pigment absorption feature that we're looking at. 685 is the base of the pigment absorption feature. This is all in the visible, and we go up into the infrared here. This is typically what we see. This represents changes in chlorophyll and carotenoids based on health. Increase our prediction of growth on these sites to 0.75, which is a pretty reasonable model, and reduce the root mean square from 1.3 to 0.89 millimeters per year. And then we also map biomass using that as well. So we can use the two of them. It's like I said, it's an incremental improvement in output by incorporating the two, as long as the two have what we hopefully will be doing this year. We'll be flying about 3,000 to 4,000 square kilometers up in the McMurray area with all of these sensors in the fixed wing and the helicopter, and provide the data to Todd, process, available to anybody who wants it, and work with anybody who wants to work with us on this. That's it.